dependent motion. For example, here the motion of this load depends upon the motion of the cables as they're being drawn into the winch on this crane. And the same thing occurs here. Now let me show you an animation where you'll notice the motion of both blocks are different. The motion of the one block depends upon the cable arrangement and the motion of the other block. Now to show how we can relate the dependent motion of one block, which is connected to another block through a series of cables and pulleys, let's consider this simple example. I think you'll agree with me that when A moves down with this motion, B will be moving up with the same motion. That's intuitive here, but let's see if we can develop a formal procedure to prove it. The first thing we'll do is we'll set up a fixed datum, a datum that passes through a fixed point, like the point right here, where the axle of the pulley is located. If I set up my datum from here, I can then locate each of the different crates. For example, a position coordinate going from our fixed datum down to here we'll refer to as S sub A. Notice that it's positive because it goes downward. And here, of course, is another coordinate, locating this crate, and it's positive also, downward. With these two coordinates now established, I can write the entire length of the cord, can't I? That length, L, is equal to, first the segment S sub A, then the segment S sub B, and finally, we have the arc length that passes over the top of the pulley here. We'll define it using this. This is a position coordinate equation. If I find its time derivative, realize that this term will be equal to 0, because the total length of the cord remains constant with all time. Therefore, 0 will equal the derivative of this, which of course is ds sub A dt, or v of A. And that, of course, refers to the velocity of the crate at A. Now we have the same idea for B. ds sub B dt is v of B. And finally, the derivative of the arc length would be equal to 0. We now have a velocity equation, an equation that relates the velocity of A to the velocity of B. And if I solve for v of B here, I get the following. V of B is equal to minus V of A. But V of A is defined as positive 2. Positive because it's going down in the direction of our positive coordinate. And therefore, if I put that in here, I'll get my answer for V of B. And it turns out to be equal to minus 2, doesn't it? Minus 2 means that B is moving upward in this direction at 2 meters per second. I've shown that here with a little arrow to indicate that direction. If I want to find the relationship between the accelerations, I have to take the time derivative of this equation. And there, of course, I think you'll see that A of B will equal minus A of A. Substituting A of A as plus 5, I get A of B equaling minus 5. What does that mean? That's right, it moves upward at 5 meters per second squared. Finally, let me go back and discuss this a little bit more. We don't need to really find the total length of the cable when we write our position coordinate equation. We simply have to look at the lengths that are changing. In other words, there's no need to add on the arc length over the top of the pulley. We can simply just write it as the vertical segments. In other words, these two segments of cord are changing lengths, but the total length of both of them must be equal to some length L prime. But it's a constant amount, and when you take its derivative, it always winds up to be 0. So here's a formal way in which we can actually solve these kinds of problems. The first thing is to establish a position coordinate measured from a fixed datum to each one of the blocks in a system of pulleys and blocks and cables. The second thing is to use geometry or trigonometry to relate the length of the cord to the position coordinates. And next, you take the time derivative of the position coordinate equation to obtain the relationships between the velocities and the accelerations of the blocks. Now let's apply the idea further to a few more problems to really make sure you understand how it's done. In solving this problem and trying to find the velocity of the block at B, what would you do first? Sure, you find a fixed point on the system, like right here, and you set up a fixed datum. Now we have to measure the vertical segments of our cable, don't we? Here we go to point A and define its location using a position coordinate S sub A. Now how are we going to locate B? Well, we can come right here, can't we? So here's a position coordinate that will locate this point. When we know the speed of it, we'll know how fast block B is moving. We'll refer to this coordinate as S sub B. The only thing we have to worry about now is finding the vertical length of these cable segments and write an equation to show that total length, of course, is equal to a constant L. So we write the following. L is equal to what? Well, S sub A, and what else? Plus 2 times S sub B. And again, we don't need to include the arc length down here or the length up here to write the total length, because the time derivative of this equation will give us zeros for those changes of length, which of course it should because it's always constant. But again, these vertical segments will change length with time, but the total length will be equal to the same constant amount. Anyway, taking the time derivative of this, we have 0 equaling V of A plus 2 times V of B. Next, we solve for V of B. And of course, when we do that, we see that it's equal to minus V of A divided by 2. If I substitute V of A in here, I would put plus 6, wouldn't I? Because it's going downward in the direction of our positive position coordinate direction. And so therefore this becomes minus 6 divided by 2. When you solve this, of course, you get minus 3 meters per second. Minus 3 meters per second means that the block is moving upward in the negative S sub B direction. And I show that next to my answer. Now let's consider this one. Here we want to find the velocity of this block when this cord is pulled down at 8 meters per second. So what do we do first? That's right, we set up a fixed datum and we'll do it right through here. Now we have to locate both A and B. Do you see the location for A? It'd be right like this, wouldn't it? S sub A. And what about B? Here it is, S sub B. Now we have to worry about the changing lengths, which is simply this and this. So we write L equaling S sub A plus S sub B. What about this piece right in here? Well, as time passes, it doesn't change length whatsoever, does it? And so we don't need to include that in our length L here. Anyway, taking the time derivative of this equation now, we get our relationship between A and B. And here, of course, we get 0 equaling V of A plus V of B. And since we know what V of A is, it's 8, we can see that V of B is equal to minus V of A, or minus 8. And of course, that's meters per second. And the negative sign again says that B is moving upward, as you would expect, in the negative S sub B direction. All right, now let's consider a problem like this one. And here's a graphic of the same problem. We want to determine how fast is this crate moving when this one is going upward at 6 meters per second. So we set up our fixed datum, and you would expect it to probably go right through here. And from here we measure the location of A and B. Here's S sub A, positive downward. and now S sub B. Also positive downward. Now we write the entire length of the vertical segments of the cable that's changing length. That would be all of this, wouldn't it? So we have L equaling 2 S sub A plus S sub B. Taking our time derivative, 0 is equal to 2 times V of A plus V of B. And now we substitute in the data. What would you put in for V of A? Well, of course, that would be equal to minus 6, right? Because it's going up instead of down. So if I do that and I solve for V of B, this is minus 6 times 2, of course, bring it on the other side, and we get the result of plus 12. Of course, it's meters per second. Positive 12 means that B indeed moves downward, just like we see here. So having completed the problem, now we'll end our lesson.